Look up at the night sky, and what do you see? A handful of stars, a distant planet, maybe the faint glow of the Milky Way if you're lucky. But what if I told you that everything you see, everything you think you know about the universe, barely scratches the surface of its true strangeness? The cosmos is packed with secrets so bizarre they sound like science fiction. Black holes that sing, galaxies made of dark matter, parallel universes that might exist just beyond our reach. And that's only the beginning. Picture this: every atom in your body was forged in the heart of a dying star. You are, quite literally, made of stardust, a living, breathing piece of the universe's grand story. But here's the thing: the more we learn about space, the more it feels like we're peeling back layers of an infinite onion. Just when we think we've got it figured out, the cosmos throws us another curveball. Like the fact that 95% of the universe is missing, or that time itself might flow backward in some corners of reality. Sounds impossible, right? Yet these are the truths scientists are uncovering right now. That's exactly what we're diving into today: 30 of the most mind-bending, reality-shaking facts about the universe that will make you question everything. From the eerie silence of empty space to the possibility that we're all living inside a cosmic hologram, these aren't just fun trivia. They're clues to the deepest mysteries of existence. So whether you're a space enthusiast or just someone who loves a good "wait, what?" moment, stick around. By the end of this, the night sky will never look the same to you again. Right now, all the planets, stars, and galaxies we've ever observed, everything visible through telescopes, amounts to less than 5% of the universe. The rest, it's utterly invisible. We call it dark matter and dark energy, two cosmic mysteries that defy everything we thought we knew about reality. Dark matter doesn't emit light or energy, and dark energy is even stranger, an unknown force stretching the fabric of space itself. Yet together, they dominate the cosmos, shaping galaxies and accelerating the universe's expansion. Here's how we know they exist. Imagine spinning a merry-go-round so fast that the kids clinging to it should fly off, but instead, they stay glued in place as if invisible hands are holding them. That's what happens in space. Galaxies rotate so quickly that their stars should scatter into the void, yet something unseen, dark matter, anchors them with its gravity. Then there's dark energy, the reason the universe isn't just expanding, but doing so faster and faster, like a loaf of bread baking in an oven that's inexplicably heating up on its own. The craziest part, we have no idea what these forces actually are. Dark matter could be particles unlike anything we've discovered, or entire hidden dimensions curdling through the cosmos. Dark energy might be a property of space itself, or evidence of parallel universes pushing against ours. Every experiment so far has come up empty. Dark matter slips through detectors like a ghost, and dark energy remains a mathematical shadow. This isn't just a gap in our knowledge, it's a cosmic-sized hole. Think of it like standing in a pitch-black room, knowing 95% of the room's contents are right in front of you, invisible, untouchable, but undeniably there. The universe isn't just stranger than we imagined, it's stranger than we can imagine, and the hunt to uncover its hidden layers, that's the greatest detective story in science. Time behaves differently in the presence of a black hole, not like the steady, predictable ticking of a clock, but as a warped, stretchable fabric. Einstein's theory of relativity revealed this over a century ago, yet it still feels like something ripped straight from a sci-fi novel. Near a black hole where gravity is so intense that not even light can escape, time slows to a crawl. For someone watching from a safe distance, a person falling toward the event horizon would appear to move in slow motion, their signals stretching out like taffy. But for the person actually falling, time would feel perfectly normal. This bizarre phenomenon is called time dilation, and it's not just theoretical. GPS satellites orbiting Earth have to account for it because even our planet's weaker gravity speeds up time ever so slightly compared to the surface. Think of it like two clocks, one placed at the top of a skyscraper and the other at ground level. Over time, the higher clock ticks slightly faster because it's farther from Earth's gravitational pull. Now amplify that effect by a factor of millions, and you've got the mind-bending reality near a black hole. The movie Interstellar got this eerily right. Remember the scene where the crew visits a planet orbiting Gargantua, the film's fictional black hole? For every hour they spend on that world, 7 years pass back on their ship. That's not Hollywood exaggeration, it's real physics. The planet's proximity to the black hole's gravitational well literally stretches time itself. Here's the kicker: this isn't just about clocks ticking differently. Time dilation means the very structure of reality is flexible. Imagine two twins, one stays on Earth while the other travels near a black hole and returns. The Earthbound twin might be an old man by the time their sibling comes back, barely aged. It's a paradox that challenges our instinctive sense of time as universal and unchanging. And it gets weirder because black holes aren't the only things that warp time. Speed does too. The faster you move through space, the slower time passes for you relative to someone standing still. Astronauts on the International Space Station experience this, aging microseconds less than people on the ground. So what's really happening? Gravity and motion both twist the fabric of spacetime, the four-dimensional mesh that underpins reality. Black holes just take it to the extreme, bending the rules so dramatically that time itself becomes fluid. Scientists have even detected this effect using telescopes, watching as stars orbiting our galaxy's central black holes seem to move in slow motion. It's a universe where the clock on your wall is a local construct, not a cosmic rule, and where the deeper we look, the more time unravels into something stranger than fiction. There's a saying that the number of stars in the observable universe exceeds all the grains of sand on every beach and desert on Earth. At first glance, that sounds like poetic exaggeration until you run the numbers. Our Milky Way alone holds roughly 100 billion stars, and astronomers estimate there are at least 2 trillion galaxies in the visible universe. Do the math and you're staring at a figure so colossal it defies comprehension. 10,000 stars for every single grain of sand on our planet. Let's put that in perspective. Picture standing on a quiet shore, scooping up a handful of sand. Even that small handful might contain tens of thousands of grains. Now imagine every one of those grains replaced by a star. Not just our familiar sun, but entire systems with planets, asteroids, and possibilities. Now take that image and multiply it by every beach, every desert dune, every speck of sand in the world. That's the scale we're talking about, not just vast, but inconceivably vast. Here's where it gets even wilder. Those 2 trillion galaxies, they're just the ones we can see. The observable universe stretches about 93 billion light-years across, but beyond that horizon, space might continue endlessly. Some theories suggest the true number of galaxies could be infinite, meaning stars outnumber sand grains not by a factor of thousands, but by an uncountable margin. And yet, despite these staggering numbers, the cosmos feels eerily empty. The average distance between stars in our galactic neighborhood is about 5 light-years. That's 30 trillion miles of void between each point of light. It's like having 2 grains of sand separated by an entire football field. The universe doesn't just dwarf our imagination, it humbles it. Every time we peer deeper into the night sky, we're reminded we're not just small. We're a fleeting whisper in a story written in numbers too large for the human mind to hold. The moon isn't just hanging in the sky like a silent guardian, it's slowly slipping away from us. Every year, our closest celestial neighbor drifts about 3.8 centimeters farther into space. That might not sound like much, but over millions of years, those tiny nudges add up to a cosmic game of tug-of-war with Earth's future hanging in the balance. This slow-motion escape happens because of tides, the same ocean swells that shape our coastlines. As Earth rotates, its gravitational pull tugs the Moon forward in its orbit, while the Moon's gravity drags tides across our planet, creating friction that slows Earth's spin. Energy doesn't vanish, it transfers. Like a figure skater extending their arms to slow a spin, Earth loses rotational momentum, and that energy pushes the Moon into a higher orbit. What does this mean for us? Over time, Earth's days will grow longer. Right now, a day is about 24 hours, but 600 million years ago, it was just 22 hours. Fast forward another few hundred million years, and a single day might stretch to 25 hours, then 30, as the Moon's retreat continues. The tides will weaken too. Those dramatic ocean surges that sculpt ecosystems and power coastal currents will dwindle, leaving shorelines eerily still. And here's the real kicker: solar eclipses won't last forever. The Moon's apparent size in our sky perfectly matches the Sun's, creating those breathtaking moments of totality when day turns to night. But as the Moon drifts farther away, it'll appear smaller. In about 600 million years, it'll no longer fully cover the Sun, robbing future Earthlings of total eclipses. This isn't just a distant future problem, it's a reminder that even the most familiar parts of our universe are in constant flux. The Moon has been Earth's companion for over 4 billion years, but nothing lasts forever. One day, it'll be a faint, distant dot in the sky, and the night will never look the same again. When you step outside on a sunny day, the warmth on your skin feels instant, like the sun's light reaches you the moment it's born. But here's the twist: that sunlight is older than human civilization, much older. Every photon that touches your skin began its journey in the sun's core roughly 30,000 years ago. That's right, the light you're seeing today was created back when woolly mammoths still roamed the Earth. So why does it take so long? The sun's core is a chaotic dance of particles, where photons are constantly absorbed and re-emitted by atoms in a random walk toward the surface. Picture a crowded subway station during rush hour. You're trying to reach the exit, but every few steps someone bumps into you, sending you off course. That's what happens to light inside the sun. A photon might travel less than a millimeter before getting swallowed by a hydrogen atom and spat back out in a new direction. This game of cosmic pinball means it can take millennia for light to finally break free from the sun's dense interior. But here's where it gets even stranger. Once those photons escape the sun's surface, they bolt toward Earth at the speed of light, covering the 93 million miles between us in just 8 minutes. Think about that contrast: 30,000 years of struggle to escape, followed by a sprint so fast it could lap the Earth 7 times in a single second. This delay isn't just a fun fact, it's a window into how stars work. The sun isn't a hollow ball of light, it's a plasma powerhouse so dense that even light gets trapped in the chaos. And those ancient photons, they're messengers from a time when the Sahara was lush and green, carrying energy forged in nuclear fires that have burned steadily for billions of years. The next time you feel sunlight, remember, you're touching a relic from a world long gone, delivered across time and space in a journey more epic than any myth. Venus doesn't just orbit the sun, it defies every expectation of how a planet should behave. While Earth and most other planets spin counter-clockwise like marbles rolling around a drain, Venus spins stubbornly backward, rotating clockwise in what astronomers call retrograde motion. But here's the real shocker. A single day on Venus, the time it takes to complete one full rotation, lasts 243 Earth days, longer than its entire year. That means if you stood on Venus's scorching surface, you'd witness a sunrise only once every 117 Earth days, with the sun creeping sluggishly across the sky before taking months to set. How did Venus end up so out of sync? One leading theory points to a cataclysmic collision billions of years ago. Picture a protoplanet the size of Mars slamming into Venus with such force that it not only knocked the planet's spin into reverse but also vaporized what might have once been oceans. The impact could have been so violent that it sent Venus tumbling like a flipped coin, leaving it spinning backward in a slow, stubborn wobble. But there's another twist. Venus's thick, soupy atmosphere might share the blame. With air pressure 90 times heavier than Earth's and hurricane force, winds that whip around the planet every 4 days, this suffocating blanket could be tugging on the surface like an invisible hand, slowing its rotation over eons. Imagine trying to spin a ball in a vat of syrup. The dense fluid resists the motion, dragging it to a crawl. Venus's atmosphere could be doing the same, battling the planet's spin until it reversed course. The strangeness doesn't stop there. Because Venus rotates so slowly, its crust has time to overheat under the relentless sun, creating a landscape where temperatures soar past 800 degrees Fahrenheit, hot enough to melt lead. Yet paradoxically, its upper atmosphere is one of the most Earth-like places in the solar system, with pressure and temperatures that could almost support human life. If not for the sulfuric acid clouds, this backward-spinning enigma forces us to rethink how planets evolve. Venus isn't just a cautionary tale of runaway greenhouse effects, it's a cosmic rebel, challenging our assumptions about how worlds form and behave. Whether shaped by ancient violence or atmospheric rebellion, its peculiar spin reminds us the universe never plays by the rules we expect. When a massive star dies in a supernova, it doesn't always vanish into a black hole. Sometimes it leaves behind a celestial diamond so dense it defies logic. Meet the neutron star, a cosmic remnant where matter gets crushed into its most extreme form imaginable. Just a sugar cube's worth of this star stuff would weigh 1 billion tons on Earth, as much as a mountain packed into a speck small enough to balance on your fingertip. How does something so unimaginably heavy even exist? Picture the core of a dying star, once a churning inferno of nuclear fusion. When the star collapses, gravity squeezes its atoms so violently that electrons and protons merge into neutrons, leaving no empty space. Just a seething ball of pure atomic nuclei. The result is a city-sized object with the mass of our entire sun, spinning hundreds of times per second. If you dropped a marshmallow onto a neutron star's surface, the impact would release as much energy as a nuclear bomb. But the madness doesn't stop there. Some neutron stars become pulsars, cosmic lighthouses that blast beams of radiation across the galaxy. Their gravity is so intense it bends light into a narrow cone, and as the star spins, these beams sweep past Earth like the strobe of a disco ball. The fastest known pulsar, discovered in 2006, spins 716 times per second, so rapid, its surface moves at nearly a quarter the speed of light. Then there's the magnetism. Certain neutron stars, called magnetars, wield magnetic fields a quadrillion times stronger than Earth's. If a magnetar floated halfway between Earth and the Moon, its pull would erase the data from every credit card on the planet. These fields are so powerful they can crack the star's crust in starquakes, releasing bursts of gamma rays visible across the universe, the wildest part. Neutron stars might be hiding even stranger secrets. Some theories suggest their cores contain quark-gluon plasma, a state of matter so exotic protons and neutrons dissolve into a soup of subatomic particles. Others speculate that collisions between neutron stars forge gold, platinum, and other heavy elements, sprinkling the cosmos with the ingredients for jewelry and electronics. These stellar diamonds aren't just cosmic oddities, they're laboratories for physics under conditions we could never replicate on Earth. Every pulse, every quake, every flicker of light carries clues about the universe's most extreme forces. And the next time you look up at the night sky, remember, somewhere out there, a tiny, spinning diamond is bending the very fabric of reality. If you could take a deep breath in deep space, you might catch a whiff of something unexpected: raspberries. Yes, that's right. The universe in all its infinite vastness has pockets that smell like a cosmic dessert. Astronomers discovered this bizarre twist when they detected ethyl formate in a giant gas cloud near the center of our galaxy. This molecule just happens to be the same chemical that gives raspberries their sweet, fruity aroma and rum its distinctive kick. So how does this interstellar berry scent even exist? Picture a sprawling nursery of gas and dust where new stars are born, swirling with raw ingredients like carbon, hydrogen, and oxygen. Under the right conditions, these atoms link up into complex molecules, including ethyl formate. It's like a celestial kitchen where random ingredients somehow bake into familiar flavors. But here's the catch. While the cloud might technically smell like raspberries, you wouldn't want to take a sniff. Mixed with other compounds like propyl cyanide, which has the unmistakable stench of bitter almonds, the overall bouquet would be less fresh fruit and more alien brewery gone wrong. Scientists joke that Sagittarius B2, the cloud where this was found, might be the universe's way of mixing a cocktail we're not quite ready to drink. The real magic here isn't just the whimsy of space raspberries, it's what this reveals about cosmic chemistry. The fact that organic molecules like ethyl formate form so easily in the void suggests something profound. The building blocks of flavor, fragrance, and even life itself might be scattered everywhere. The same processes that craft a raspberry scent in a lab on Earth are happening unaided in the depths of space. It makes you wonder, if the universe can accidentally brew up the essence of fruit and rum, what other familiar or utterly alien scents are drifting out there unseen? Maybe somewhere a distant nebula smells like freshly baked bread, or a star's fiery corona carries the sharp tang of peppermint. The cosmos is clearly a far more aromatic place than we ever imagined. Deep in the constellation Boötes lies one of the universe's most unsettling mysteries, a yawning chasm of nothingness so vast it could swallow thousands of galaxies whole. The Boötes void stretches 330 million light-years across, a cosmic desert where galaxies are so sparse you could fly for millions of years without seeing a single star. Out of the 60 galaxies expected in a space that size, astronomers have found only a handful. It's as if someone took an eraser to the universe, scrubbing away matter on a scale that defies explanation. So what carved this gaping hole in the cosmos? One theory points to quantum fluctuations in the early universe, tiny ripples in the fabric of reality that, when stretched by cosmic inflation, left some regions bizarrely empty. Imagine blowing up a balloon with a few weak spots. As it expands, those thin patches grow into enormous voids. But the Boötes void isn't just empty, it's too empty. Even the most conservative models struggle to account for its sheer scale, leading to wilder speculation. Could advanced civilizations have harvested every scrap of matter here, leaving behind a galactic ghost town? It sounds like science fiction, but the Kardashev scale, a method of ranking a civilization's energy use, suggests that Type 3 civilizations might harness the power of entire galaxies. If such beings existed, the void could be their footprint. Here's the twist: the void isn't completely barren. The few galaxies that do exist there are strangely clustered together, like survivors huddling on an island in an endless ocean. Some gleam with unusual blue hues, suggesting frantic star formation, as if they're desperately rebuilding after some catastrophic event. Others show signs of distortion, their shapes stretched by gravitational forces we can't yet explain. The Boötes void forces us to confront how little we understand about the universe's structure. Voids like this aren't rare, but none match its staggering emptiness. Is it a statistical fluke, a relic of cosmic violence, or evidence of something far stranger? Until we peer deeper into its darkness, one thing's certain: the universe isn't just vast. It's full of holes we can't begin to fathom. Mercury, the closest planet to the Sun, seems like the last place you'd expect to find ice, with daytime temperatures soaring to 800 degrees Fahrenheit. height hot enough to melt lead, its surface feels more like a blast furnace than a winter wonderland. Yet hidden in the depths of its polar craters, shielded from the sun's relentless glare, lie vast deposits of water ice. It's a paradox that defies intuition, a planet where you could simultaneously fry and freeze depending on where you stand. The secret lies in Mercury's extreme axial tilt, or rather, its lack of one. Unlike Earth, which tilts at 23 degrees, Mercury barely leans at all. This means some craters at its poles never see sunlight, plunging them into perpetual shadow. In these sunless pits, temperatures plummet to -300 degrees Fahrenheit, colder than Pluto. Over billions of years, comets and asteroids smashing into Mercury could have delivered water, which then became trapped in these icy vaults. Radar observations from Earth and NASA, a messenger probe, confirmed it. Reflective patches near the poles match the signature of water ice, some layers thick enough to fill thousands of Olympic swimming pools. Here's where it gets even wilder. Mercury's ice might hold clues to the solar system's history. Since the ice has likely sat undisturbed for billions of years, it could be a pristine time capsule, preserving ancient organic compounds or even hints of how water reached inner planets like Earth. Some scientists speculate that if Mercury, a world where the sun appears 3 times larger and 11 times brighter than on Earth, can hoard ice, then water might lurk in other seemingly hostile corners of the cosmos. But the real game changer is what this means for the future. Water isn't just for drinking, it's a resource for oxygen and rocket fuel. If humanity ever establishes a foothold on Mercury, these shadowed craters could become natural depots, supplying missions deeper into the solar system. Imagine a lunar-style base perched on the edge of a crater, where astronauts mine ice just steps away from sun-baked plains hot enough to vaporize metal. It sounds like science fiction, but NASA has already studied the feasibility, sketching out concepts for shielded rovers that could venture into these frozen darknesses. Mercury's ice is a reminder that the universe loves to hide its treasures in plain sight. The same planet where daytime could melt your shoes holds frozen reservoirs older than life itself. And if water can survive here on the doorstep of the sun, then perhaps the galaxy is far wetter and weirder than we ever dreamed. We've all heard it 1,000 times. Space is a silent vacuum where no one can hear you scream. But what if that's not entirely true? While it's true that sound waves can't travel through the empty void the way they do on Earth, the cosmos is far from mute. NASA spacecraft have captured something even stranger: electromagnetic vibrations from planets, stars, and magnetic fields, converted into sound waves we can actually hear. The result, a symphony of eerie, otherworldly noise that redefines what it means to listen to the universe. Take Saturn, for example. When NASA Cassini probe dove between the planet and its rings, it detected plasma waves rippling through the magnetic field. Scientists translated these oscillations into audio, and what came back sounds like a horror movie soundtrack, a chorus of ghostly wails, hisses, and static that would make your hair stand on end. Or consider Jupiter's moon, Ganymede. Recordings from the Juno spacecraft reveal a series of rapid clicks and pops, like an alien Morse code tapping against the icy crust. These aren't just random noises, they're the voices of charged particles dancing in magnetic fields, a hidden soundscape we've only just begun to decode. But the real showstopper, the black hole at the center of the Perseus galaxy cluster. For years, astronomers assumed it was surrounded by perfect silence until they realized the superheated gas swirling around it creates pressure waves. In 2003, NASA sonified those waves, shifting them up 57 octaves to make them audible to human ears. The sound is a deep, resonant hum, like the lowest note on a piano played for 250 million years. It's the oldest song in the universe, a single, unbroken tone echoing across cosmic time. Here's the twist: these sounds aren't just scientific curiosities. Their tools, by listening to space, astronomers can map invisible forces like magnetic fields or plasma densities in ways telescopes can't. The eerie screeches of Earth's own magnetosphere, for instance, warned scientists about incoming solar storms before they hit. It's as if the universe is whispering its secrets not in light but in vibrations. So the next time someone says space is silent, you'll know better. The cosmos might not sound the way we expect, but it's humming, crackling, and singing in ways we're only starting to hear. And who knows, maybe one day we'll tune into a frequency that reveals something we never saw coming. The Milky Way seems like a tranquil island of stars, but beneath its serene glow lies a violent past and future. Our galaxy didn't grow by chance, it devoured its neighbors. Over billions of years, the Milky Way has acted like a cosmic predator, tearing apart smaller galaxies and absorbing their stars. Right now, it's in the process of swallowing the Sagittarius dwarf, a tiny galaxy caught in its gravitational jaws. You can actually see the aftermath strewn across the night sky. Streams of stars ripped from this doomed galaxy, swirling around the Milky Way like cosmic spaghetti. This isn't just ancient history. Astronomers have mapped at least a dozen such stellar streams, ghostly remnants of past meals, wrapped around our galaxy like celestial scars. One of the most dramatic mergers happened around 8 to 10 billion years ago, when a galaxy called Gaia Enceladus, or the Sausage Galaxy, thanks to its stretched shape, slammed into the Milky Way. The collision was so violent, it sent stars careening into chaotic orbits, permanently altering our galaxy's structure. Today, we can still spot Gaia Enceladus's survivors, stars moving backward compared to the rest of the Milky Way like swimmers fighting a tide. But the feast isn't over. In about 4.5 billion years, the Milky Way will collide with its largest prey yet, the Andromeda Galaxy. Computer simulations show the two galaxies locking in a gravitational dance, spiraling closer until their stars intermingle. Unlike star collisions, which are vanishingly rare, their immense black holes will eventually merge, sending ripples through space-time. The result, a new hybrid galaxy some astronomers call Milkdromeda, its shape forever altered by the cosmic feast. Here's the eerie part: this galactic cannibalism isn't unique. It's how all large galaxies grow. The universe operates on a brutal rule. Bigger galaxies consume smaller ones, a process astronomers call hierarchical merging. Even our sun might be an immigrant, its ancestors stolen from a devoured dwarf galaxy. So the next time you gaze at the Milky Way, remember, its beauty is built on destruction, and its future is written in the stars it swallows. Jupiter's Great Red Spot isn't just a storm, it's a solar system icon, a swirling hurricane twice the width of Earth that's raged for at least 400 years. When astronomers first trained telescopes on it in the 1600s, the spot was so enormous you could fit 3 Earths side by side inside its crimson whirl. But recently, something unsettling has happened. This ancient tempest is shrinking faster than anyone predicted. Measurements show it's now barely large enough to swallow our planet whole, and its once oval shape has morphed into a squashed circle like a deflating ball. What's strangest isn't just the shrinking, it's the pace. Between 1800 and 1980, the spot lost only about 30% of its size. But since 2012, it's been shedding 15 miles of width every year, accelerating toward an uncertain fate. Some scientists think turbulent jet streams are nibbling at its edges, while others suspect deeper atmospheric changes are starving the storm of energy. Like a dying fire deprived of oxygen, the spot might be choking on Jupiter's shifting winds. Here's why this matters: the Great Red Spot isn't just a pretty feature. It's a planetary stabilizer, acting like a colossal pressure valve. It helps regulate Jupiter's chaotic weather systems by absorbing and redistributing energy. If it vanishes, the planet's banded jet streams could unravel into unpredictable patterns, triggering storms so violent they'd dwarf anything in Earth's history. Already, researchers have spotted new white ovals forming near the spot, younger, smaller tempests that might inherit its role in Jupiter's atmospheric ballet. Will it disappear entirely? Some models suggest it could stabilize at a smaller size, sustained by deeper layers of rotating gas we can't yet observe. Others warn it might dissolve within our lifetimes, leaving Jupiter's face unrecognizable to future astronomers. Either way, the spot's decline offers a front-row seat to planetary evolution. Imagine witnessing the end of a storm that predated the telescope's invention, one that outlasted every human empire, only to fade away as we watch. It's a humbling reminder, even the mightiest forces in our solar system are fleeting. Deep in the constellation Cancer, orbiting a star 40 light-years away, there's a world that would make a jeweler's heart race: 55 Cancri E, a planet where the very ground beneath your feet might glitter with diamond. Twice Earth's size and 8 times its mass, this scorching inferno isn't just carbon-rich. It's a pressure cooker where atoms rearrange into something extraordinary. Scientists estimate that a third of the planet's mass, roughly 3 Earths' worth, could be crystalline carbon. That's more diamond than has ever been mined in human history, compressed into a single, seething sphere. But don't pack your space pick just yet. 55 Cancri E orbits so close to its star that a single year lasts just 18 hours, and surface temperatures soar above 4,000 degrees Fahrenheit, hot enough to vaporize platinum. The diamond here isn't the clear, faceted gem we know. It's likely a chaotic lattice mixed with graphite and other carbon forms, forged in pressures so intense they distort the very rules of chemistry. Imagine a planet where it rains molten diamond, where mountains might be giant, shimmering crystal shards glowing red-hot under a perpetual sunset. Here's the cruel irony: even if we could reach it, mining 55 Cancri E would be pointless. Earth's diamond market relies on scarcity, but this planet's abundance would make gems as worthless as sand. A single cargo load could crash global economies overnight. And that's ignoring the logistics: landing on a world with gravity twice Earth's, where the soil might be as hard as neutron star matter, and the atmosphere, if it exists at all, could be vaporized rock. Yet the real value of 55 Cancri E isn't in its bling. It's in what it teaches us about planet formation. Most worlds in our solar system are oxygen-rich, with silica and iron dominating their crusts. But carbon planets like this one hint at a universe far more chemically diverse than we imagined. Around stars with higher carbon-to-oxygen ratios, entire planetary systems could be built from diamond, graphite, and carbides, with tar-like oceans or methane skies. This glittering oddball forces us to rethink what's possible. If diamonds can form on a planetary scale, what other impossible-seeming worlds are out there? Planets with sapphire clouds, rubies the size of continents. The cosmos has already proven it's stranger than fiction, and 55 Cancri E is just the sparkle on the surface. The universe isn't just expanding, it's keeping receipts. Everywhere you look, no matter how empty space appears, there's a faint but unmistakable glow left over from the Big Bang itself. We call it the cosmic microwave background, or CMB, and it's the oldest light in existence, stretched and cooled over 13.8 billion years until it registers just 2.7 degrees above absolute zero. That's colder than liquid helium, colder than the deepest voids between galaxies, yet it blankets the entire cosmos like an invisible thermal fingerprint. This afterglow wasn't always microwaves. In the universe's first fiery moments, it was a blistering plasma so dense and hot that light couldn't travel more than an atom's width before scattering. But as space expanded and cooled, about 380,000 years after the Big Bang, electrons and protons finally combined into atoms, clearing the fog. Light that had been trapped suddenly raced free in every direction. The moment that light escaped is what we're seeing now, redshifted by the universe's expansion from visible wavelengths into the microwave spectrum. The most astonishing part, that 2.7 Kelvin temperature isn't perfectly uniform. Tiny fluctuations, just 1 part in 100,000, reveal themselves in the iconic CMB map, a speckled blue and gold snapshot often called the baby picture of the universe. Those imperfections are cosmic gold. They represent density variations in the early universe, the seeds from which all structure galaxies, stars, even you, would eventually grow. Without those microscopic ripples, gravity would have had nothing to amplify, and the cosmos might have remained a featureless soup forever. Scientists have scrutinized this map like a Rosetta Stone of cosmology. The patterns tell us how much ordinary matter, and dark energy the universe contains. They confirm the age of the cosmos to astonishing precision. Some even hint at wilder possibilities, like collisions with other universes during inflation. Yet for all we've learned, the CMB still holds mysteries. Why is one half of the sky slightly warmer than the other? Could that be evidence of a pre-Big Bang universe, or is it just the ghostly imprint of our own motion through space-time? What's clear is this: every time you tune an old analog TV to static, about 1% of that snow comes from the CMB. You're literally seeing whispers of creation itself, filtered through decades of electronics. The universe left its temperature everywhere, not as a monument but as a message, and we're only beginning to decode it. Saturn's dazzling rings might look eternal, but they're actually cosmic newborns barely 100 million years old. That means when Tyrannosaurus Rex stomped through prehistoric forests, Saturn's iconic jewelry hadn't even formed yet. The evidence comes from Cassini's final act. As the spacecraft plunged toward Saturn in 2017, it measured the ring's mass with unprecedented precision. Turns out they're far too lightweight to have existed for billions of years. Cosmic dust and micrometeoroid bombardment should have darkened them over time, yet they gleam unnaturally bright, like a freshly fallen snowfield untouched by soot. So where did they come from? The leading theory involves a tragic moon. Picture an icy satellite orbiting too close to Saturn, its gravity stretching until tidal forces rip it apart. Or perhaps a comet slammed into a moon, shattering it into countless frozen fragments. Either way, the debris got caught in Saturn's gravitational dance, spreading into the magnificent rings we see today. It's a reminder that even the most serene celestial vistas can be born from violence. But here's the catch: these rings are living on borrowed time. Saturn's gravity is slowly devouring them, pulling material down as icy rain. The innermost rings lose the equivalent of an Olympic-sized swimming pool's worth of water every half hour, enough to fill Earth's oceans in 300 million years. Future astronomers might gaze at Saturn through telescopes and see only ghostly, threadbare arcs. Eventually, the rings will vanish entirely, leaving Saturn naked for the first time in its history. The irony is poetic. We think of planets as timeless, yet Saturn's most famous feature is both younger than the dinosaurs and destined to fade. It's a fleeting masterpiece, a reminder that even the grandest cosmic wonders have expiration dates. So while we're here to witness them, let's savor the view, because in the universe's long memory, Saturn's rings are just a blink. Earth doesn't just have one moon, it has a secret companion you've never seen. Meet Camolwa, a bizarre cosmic tagalong that dances around our planet in an orbit so peculiar, scientists still debate whether to call it a second moon. This asteroid, roughly the size of a Ferris wheel, doesn't circle Earth directly like our familiar lunar neighbor. Instead, it's what astronomers call a quasi-satellite, an object that orbits the Sun in perfect sync with Earth, making it appear as though it's orbiting us from afar. Here's how the cosmic choreography works. While our moon follows a tidy elliptical path around Earth, Camolwa loops around the Sun in a twisted, corkscrew motion that keeps it perpetually near our planet. Picture two race cars on a circular track, one slightly ahead but maintaining the same speed. They'll keep passing each other without ever colliding. That's the delicate gravitational ballet this space rock performs, never straying more than about 40 times the moon's distance from us. But is it truly a moon? Some argue yes, because its motion is so tightly bound to Earth's gravity that it's effectively part of our planetary system. Others counter that it's just a temporary passenger likely to break free in a few centuries. The debate isn't just semantic, it forces us to rethink what counts as a moon. If Camolwa qualifies, then Earth has had dozens of mini-moons over its history, most lingering only months before drifting away. Then there's the mystery of its origin. Spectral analysis reveals Camolwa's surface resembles lunar rock, leading to a jaw-dropping theory. This might be a piece of our moon blasted into space by an ancient asteroid impact. If true, it means Earth's second moon could be a long-lost fragment of its first, reunited after millions of years adrift. Alternatively, it could be a captured asteroid, snared by Earth's gravity during a chance encounter. What's certain is that quasi-satellites like this aren't just curiosities, they're potential stepping stones for future space exploration. Their stable orbits and proximity make them ideal test sites for missions beyond the moon. Some scientists even speculate they could be mined for resources, acting as celestial pit stops. So keep looking up. The night sky holds more secrets than we ever imagined, and Earth's cosmic family might be bigger and stranger than we thought. Here's a truth that might make you question everything you've ever drawn as a kid. The sun isn't actually yellow. It's white, pure, unfiltered sunlight as seen from space is a crisp, brilliant white like a blazing spotlight against the inky blackness of the cosmos. So why does it look golden or orange from Earth? Blame our planet's atmosphere, which acts like a celestial Instagram filter, twisting the sun's true colors into something more dramatic. The magic, or rather, the physics happens because of something called Rayleigh scattering. When sunlight enters Earth's atmosphere, it collides with molecules of nitrogen and oxygen, scattering the shorter blue wavelengths in all directions. This is why the sky appears blue during the day, but by the time sunlight reaches your eyes at sunrise or sunset, it's traveled through so much of the atmosphere that most of the blue and even green light has been scattered away, leaving behind the longer red, orange, and yellow wavelengths. That's why the sun looks like a fiery orb near the horizon. Space doesn't play these tricks. Astronauts aboard the International Space Station see the sun for what it truly is. A white disk so blindingly bright they can't stare at it without protective filters. Side-by-side photos tell the story. From space, the sun resembles a polished marble, while from Earth, it's a softened, golden glow. Even at high noon, when the sun is directly overhead and its light passes through the least amount of atmosphere, it still appears slightly yellowish compared to its pristine space counterpart. But here's the twist: the sun's whiteness isn't just a quirk of perception. It's a clue to its temperature. Stars emit light across the entire visible spectrum, and our sun's surface burns at around 5,500 degrees Celsius, a heat that produces a balanced mix of all colors, which our eyes interpret as white. Cooler stars glow red or orange, while hotter ones shine blue. If the sun were truly yellow, it would mean it's cooler than it actually is, fundamentally changing our understanding of its physics. So why does this myth persist? Partly because culture reinforces it. From children's drawings to weather app icons, we're conditioned to depict the sun as a yellow circle with rays. Even language plays a role. We call it a yellow dwarf star, though the term refers to its classification, not its color. But next time you step outside on a clear day, remember, you're standing under a white star painted gold by the sky itself. It's not just a trick of the light, it's proof that reality is often stranger than the stories we tell about it. Imagine floating in the weightlessness of space, free from the constant pull of gravity, only to return home and discover you've outgrown your favorite pair of pants. It sounds like science fiction, but for astronauts, this bizarre reality is just another day at the office. In microgravity, the human body can stretch up to 2 inches taller, a temporary growth spurt that comes with a painful catch. Here's how it works. On Earth, gravity compresses your spine like a coiled spring, squeezing the cartilage between your vertebrae. But in space, without that downward force, your spinal discs expand, creating small gaps between each bone. Over weeks or months, this subtle decompression can add significant length to your stature. Astronauts aboard the International Space Station often joke about the novelty of looking down at their normally taller crewmates until they remember the price they'll pay when gravity reasserts its grip. The return to Earth is where the real discomfort begins. Just as your spine stretched in microgravity, it collapses back to its original size under the renewed weight of gravity, often causing excruciating back pain. Imagine the ache of a long-haul flight multiplied by 10 muscles weakened by months of disuse, now straining to support a suddenly compressed skeleton. Some astronauts describe it as feeling like a vice tightening around their spine, while others report shooting nerve pain as their vertebrae realign. This isn't just an oddity of space travel, it's a stark reminder of how deeply gravity shapes our bodies. Without its constant pressure, bones lose density, muscles atrophy, and even the fluid distribution in your body shifts, creating a puffy space face as fluids migrate upward. Yet while most of these changes reverse post-flight, some studies suggest prolonged spinal stretching in microgravity could contribute to long-term back problems, a sobering trade-off for those extra inches. The irony, that brief taste of extra height is a fleeting illusion, a cosmic prank played by physics. Next time you wish you were taller, just remember, the universe offers a way, but the fine print includes zero gravity and a world of hurt when you come back down. The Andromeda Galaxy isn't just our closest galactic neighbor. It's on a collision course with our own Milky Way, barreling toward us at 250,000 miles per hour. In about 4 billion years, these two cosmic titans will meet in a slow-motion merger so vast it defies human timescales. But don't panic, this isn't the apocalyptic smash-up it sounds like. Galaxies are mostly empty space, so when they collide, stars rarely crash. Instead, they'll perform an intricate gravitational dance, weaving past one another like swarms of fireflies in the night. The first contact will be almost poetic. As Andromeda's gravitational pull tugs at the Milky Way, our spiral arms will begin to warp and stretch like taffy pulled by an invisible hand. Over millions of years, the two galaxies will loop around each other, their stars scattering into chaotic new orbits. Computer simulations show this as a breathtaking celestial ballet, streams of stars flung outward, forming long, shimmering tidal tails that glow against the darkness. The Milky Way's neat spiral structure will dissolve, replaced by a turbulent sea of stars caught in a cosmic whirlpool. But the real magic happens after the first pass. Gravity will eventually draw the galaxies back together, and this time they'll merge for good. Over another billion years, their stars will settle into a single, bloated elliptical galaxy that astronomers have nicknamed Milkomda. The night sky from any surviving planets will be transformed. Instead of the Milky Way's starry ribbon, future inhabitants might see a diffuse golden haze, the combined glow of two galaxies' worth of stars packed into a shapeless cloud. Here's the twist: while stars won't collide, the supermassive black holes at the centers of both galaxies definitely will. The Milky Way's 4 million solar mass black hole and Andromeda's 100 million solar mass beast will spiral toward each other, flinging stars aside like bowling pins. When they finally merge, the impact will send ripples through space-time itself, gravitational waves powerful enough to distort the fabric of the universe. This isn't just a future spectacle, it's already in motion. The light we see from Andromeda tonight left its stars 2.5 million years ago, and in that time the galaxy has crept millions of miles closer. By the time the merger begins, our sun will still be shining, though likely as a red giant, baking Earth to a crisp. Humanity might be long gone or evolved beyond recognition, but the universe will keep turning. Two galaxies become one, not with a bang, but with a slow, inevitable embrace. Think the universe is all black holes and burning stars. Think again. Hidden near the heart of our galaxy, there's a cloud of booze so massive it could supply every Earthling with a lifetime of cocktails. Sagittarius B2, a vast molecular cloud 25,000 light-years away, contains enough ethanol, the same alcohol found in beer and spirits, to fill 400 trillion pints. That's enough for every person on Earth to drink 300,000 drinks a day for 1 billion years. But before you start drafting your intergalactic bar crawl plans, there's a catch. This cosmic liquor store is colder than the darkest Antarctic winter, with temperatures hovering around -200 degrees Celsius. Pour yourself a glass from this cloud, and it wouldn't just be chilled, it'd be frozen solid before it even hit the rim. And that's if you could scoop any of it up, considering the cloud is mostly spread thin across the void, with molecules spaced so far apart, you'd need to process volumes larger than planets just to fill a shot glass. How did all this alcohol get there? The answer lies in the chemistry of star-forming regions. Sagittarius B2 is a nursery for new stars, packed with raw ingredients like carbon, hydrogen, and oxygen, the same elements that make up ethanol on Earth. When these atoms collide in the cold emptiness of space, they sometimes stick together, forming complex molecules. Over millions of years, these reactions built up staggering quantities of ethanol, along with other organic compounds like formaldehyde and vinegar like acetic acid. But here's the twist: this isn't just a quirky cosmic fact. Clouds like Sagittarius B2 are essentially giant chemistry labs, proving that the building blocks of life, and yes, even party supplies, can form spontaneously in the void. Some scientists speculate that similar clouds could have seeded early Earth with organic molecules, kickstarting the chain of reactions that eventually led to life. So next time you raise a glass, remember, the universe might have been mixing drinks long before we ever stumbled onto the scene. Cheers to that. Uranus doesn't orbit the sun so much as it rolls around it like a cosmic bowling ball knocked on its side. While most planets spin like tops as they circle the star, Uranus does something far stranger. It rotates at a jaw-dropping 98-degree tilt, essentially rolling along its orbital path with its north pole pointed almost directly at the sun. This bizarre configuration gives the planet the most extreme seasons in the solar system: 21 years of uninterrupted daylight followed by 21 years of crushing darkness, with only a brief twilight in between. How did Uranus end up sideways? The leading theory involves a planetary scale collision so violent, it literally knocked the world off its axis. Picture a protoplanet 2 to 3 times the mass of Earth slamming into Uranus billions of years ago, hitting with enough force to send it tumbling. Computer simulations show such an impact could have reshaped the planet's rotation, while also explaining another oddity: Uranus's icy core is strangely off-center, as if something gouged out part of its interior. Some scientists speculate the impactor might still be out there, flung into deep space after the cataclysm, leaving Uranus as the solar system's ultimate billiard ball. But there's another, wilder possibility: gravitational chaos. Early in the solar system's history, Uranus might have had a massive moon that destabilized its orbit. Over time, tidal forces could have dragged the planet sideways, much like how Earth's moon slows our rotation. Eventually, the hypothetical moon might have been ejected into space or crashed back into Uranus, leaving behind no trace except this bizarre tilt. The consequences of this sideways spin are staggering. During solstice, one pole bakes under constant sunlight while the other plunges into frigid darkness, creating temperature swings of over 50 degrees Celsius. The planet's weather patterns spiral vertically instead of horizontally, generating winds that rip across its surface at 500 miles per hour. Even Uranus's magnetic field is askew, offset by 60 degrees from its rotational axis, creating a magnetosphere that corkscrews through space behind the planet like a twisted wake. What's truly mind-bending is how this tilt affects time itself on Uranus. A single day, the time it takes to complete one rotation, lasts just 17 hours, but because of the extreme axial tilt, the Sun traces bizarre, looping paths across the sky. Near the poles, the star would spiral upward for years before finally dipping below the horizon, only to rise again 2 decades later. It's a world where compasses spin uselessly, and the very concept of up changes over geologic time. Uranus's peculiar role forces us to rethink how planets evolve. Most of our solar system's worlds share roughly similar alignments, their orderly spins hinting at a calm formation. But Uranus, it's the solar system's rebel, a reminder that cosmic violence shapes worlds in ways we're only beginning to understand. The next time you picture the planets, remember, one of them isn't just orbiting, it's doing celestial somersaults on a scale we can barely fathom. Venus doesn't just break the rules of planetary motion, it shreds them entirely. While Earth takes a brisk 24 hours to complete a single rotation, Venus drags its feet, spinning so slowly that a full day there lasts 243 Earth days. But here's the cosmic irony. Its year, the time it takes to orbit the Sun, is only 225 days. That's right, on Venus, a day is longer than a year. If you lived there, you'd celebrate your birthday before you'd even finished a single sunrise to sunset. This snail's pace spin isn't the only oddity. Venus's thick, toxic atmosphere whips around the planet at hurricane speeds, a phenomenon called superrotation. While the surface takes months to complete a single rotation, the upper atmosphere races around the planet every 4 Earth days, with winds screaming at 225 miles per hour faster than the planet itself turns. Imagine a carousel where the horses gallop so fast they lap the platform before it completes one full spin. That's the chaotic ballet happening above Venus's scorching plains. Why does this happen? The sheer density of Venus's air, 90 times heavier than Earth's, acts like a cosmic engine. Sunlight heats the atmosphere at the equator, creating colossal pressure differences that drive these supersonic winds. Meanwhile, the planet's sluggish rotation fails to counteract the momentum, allowing the atmosphere to outpace the ground below. It's as if the planet's skin is stuck in molasses while its cloak billows in a hurricane. The consequences are surreal. If you stood on Venus ignoring the 800-degree heat and crushing pressure, you'd witness a sun that rises in the west and sets in the east, but only once every 117 Earth days, crawling across the sky like a slow-motion sunset. Meanwhile, the sky itself would howl with winds strong enough to circle the planet before you'd taken a single step. This blistering, backward world forces us to rethink how atmospheres and planets interact. Venus isn't just a cautionary tale of runaway greenhouse effects, it's a laboratory for extreme physics, where the very air rebels against the ground beneath it. And every time we study it, we're reminded the universe doesn't just defy expectations, it rewrites them entirely. The moon might look like a silent, lifeless rock, but beneath its cratered surface, it's alive with tremors. Apollo astronauts left seismometers on the lunar surface in the 1970s, and what they recorded shattered expectations. The moon experiences quakes just like Earth, some strong enough to register up to 5.5 on the Richter scale. But these aren't your typical earthquakes. Lunar tremors come in 4 bizarre flavors, each more unexpected than the last. First, there are shallow moonquakes, rippling just a few miles below the surface with no clear cause. Unlike Earth's quakes, which stem from shifting tectonic plates, the moon's crust is a single, rigid shell. So what's shaking it? Scientists suspect these tremors might come from ancient faults, remnants of a time when the moon's interior cooled and shrank, wrinkling its crust like a raisin. Then there are deep moonquakes originating 400 miles down near the lunar core, triggered by Earth's gravity pulling on the moon like an invisible leash. But the strangest of all are thermal moonquakes. Every lunar morning, as sunlight first hits the surface after 2 weeks of frigid darkness, the sudden temperature swing from -200 degrees Celsius to over 100 makes the soil and rocks expand violently, cracking and popping like ice cubes in hot tea. The Apollo seismometers picked up these rhythmic tremors like clockwork, a daily groan from a world waking up. The implications for future lunar bases are staggering. While moonquakes last longer than earthquakes, sometimes vibrating the ground for 10 minutes straight, they're usually weaker. Still, in the moon's low gravity, even a moderate tremor could send loose regolith sliding like quicksand, threatening habitats or equipment. NASA Artemis missions are already mapping fault lines, searching for stable ground to build on. One proposed solution, setting up base near the poles where temperature swings are less extreme and quakes are rarer. The real surprise, some moonquakes might be useful. Just as geologists use earthquakes to probe Earth's interior, lunar tremors could reveal secrets about the moon's core and mantle. Are there pockets of molten rock deep below, clues to why the moon's magnetic field vanished billions of years ago? Every rumble is a message from a world we're only beginning to understand. So the next time you gaze at that serene white orb, remember, it's not just a silent companion. It's a world that shakes, shudders, and still has stories to tell. What if everything you see, the stars, the planets, even your own hands, isn't truly three-dimensional, but an incredibly detailed projection like a cosmic hologram? This isn't the plot of a sci-fi movie. It's a cutting-edge theory gaining traction among physicists. They call it the holographic principle, and it suggests that our entire universe might be encoded on a two-dimensional surface at the very edge of reality, with the 3D world we experience just an elaborate illusion. The idea first emerged from a paradox about black holes. When matter falls into one, it vanishes from our universe, seemingly erasing information, which violates a fundamental law of quantum physics. In the 1970s, physicist Jacob Bekenstein calculated that the maximum amount of information a black hole can hold isn't proportional to its volume, but to its surface area. In other words, everything inside could be stored on its event horizon, like data on a celestial hard drive. This led to a radical notion: what if reality itself works the same way? That the three-dimensional universe we perceive is just a projection of information encoded on a distant, two-dimensional boundary. Think of it like watching a 3D movie. The images appear to have depth, but they are actually flat pixels on a screen, precisely arranged to trick your brain. The holographic principle takes this further, suggesting the entire cosmos might operate similarly. Your senses tell you you're moving through a voluminous world, but at the most fundamental level, space could be an emergent property, a kind of optical illusion generated by quantum interactions on a flat surface we can't perceive. Here's where it gets even stranger. Some versions of string theory, a framework attempting to unify quantum mechanics and gravity, hint that space-time itself might be pixelated, built from tiny, indivisible bits at the Planck scale, much like how a digital image is made of pixels. If true, the universe could be the ultimate simulation, running on a cosmic scale processor we'll never see. Critics argue this sounds like metaphysics, but experiments are underway to test it. Certain gravitational wave detectors are searching for quantum noise in space-time, a potential signature of holographic graininess. Others study the cosmic microwave background for anomalies that might reveal an underlying code. So far, evidence is inconclusive, but the implications are staggering. If the holographic principle holds, it would mean reality as we know it is a shadow, a breathtakingly complex projection from the edge of existence. The next time you gaze at the night sky, remember, you might not just be looking at stars, you could be staring at the universe's ultimate screen. Mars isn't just home to rusty deserts and ancient riverbeds. It holds the solar system's most staggering mountain, a peak so colossal it would dwarf Everest like a speed bump. Olympus Mons rises 16 miles into the thin Martian sky, 3 times taller than Earth's highest summit, with a footprint so wide it could swallow the entire state of Arizona. This isn't just a mountain, it's a geological titan, a monument to the raw, unfettered power of Martian volcanism. What makes Olympus Mons so absurdly large? The secret lies in Mars's stagnant crust. Unlike Earth, where tectonic plates constantly shift and recycle the surface, Mars has been geologically dormant for billions of years. Here, hotspots of molten rock burn through the same patch of crust for eons, piling up lava layer by layer without interruption. Picture a pot of wax left to bubble endlessly in one spot over time. It builds into a towering, smooth-sided formation called a shield volcano. On Earth, the Hawaiian Islands are shield volcanoes, but plate movement eventually drags them away from their magma source, limiting their growth. Mars, with its frozen crust, faces no such constraint. Olympus Mons didn't just grow, it accumulated, its slopes gently rising like a frozen tsunami of basalt, until it became the tallest thing for millions of miles in any direction. Standing at its base, the summit would vanish beyond the horizon due to the planet's curvature. Climbing it would mean trekking across a slope so gradual, averaging just a 5-degree incline, that you might not even realize you're ascending until the thin air makes your head spin. And what a view awaits at the top, a caldera 50 miles wide, a nested set of collapsed pits where lava once pooled and drained, now silent under a dusty pink sky. But here's the twist, Olympus Mons might not be done. While most scientists believe it's extinct, some argue that Mars's volcanic fires could still smolder beneath the surface. Future eruptions, though unlikely, aren't off the table. Even if it never awakens, this mountain stands as a testament to a time when Mars was a world of fire, its skies choked with ash, its plains reshaped by rivers of molten rock. Next to Olympus Mons, Everest is a foothill. The solar system doesn't play by Earth's rules, and this monstrous peak is proof. HD 189,733b isn't just another exoplanet, it's a nightmare straight out of science fiction, where the skies rain molten glass sideways at 4,000 miles per hour. Located 63 light-years away in the constellation Vulpecula, this cobalt-blue gas giant looks deceptively serene from a distance, like a tranquil marble floating in space. But get closer and the illusion shatters. Here, temperatures soar to 8,000 degrees Fahrenheit, hot enough to vaporize rock, while supersonic winds blast silicate particles through the atmosphere with the force of a perpetual asteroid impact. These aren't gentle raindrops. The planet's extreme heat vaporizes silica, the same mineral found in Earth's sand, into a searing gas. As these particles collide with cooler layers of the atmosphere, they condense into tiny shards of glass, whipped horizontally by winds faster than a bullet. Imagine a sandstorm, but instead of grains of dust, the air is thick with microscopic daggers, slicing through the atmosphere in a lethal, glittering haze. Telescopes have detected traces of this glassy rain by analyzing the way light filters through the planet's toxic atmosphere, revealing a world where the very air is laced with razor-sharp crystals. But the horror doesn't stop there. HD 189,733b is tidally locked, meaning one side permanently faces its star while the other languishes in eternal darkness. The temperature difference between these hemispheres fuels those savage winds, creating a global tempest where day and night are divided by a barrage of superheated glass. If you could stand on this planet's hypothetical surface, which you can't, since it's a gas giant with no solid ground, you'd be sandblasted into oblivion before you could take a single breath. Even spacecraft would be stripped bare, their metal hulls eroded by the relentless, glass-filled gales. Strangely, the planet's sapphire hue comes from this very chaos. The same silicate particles that form the glass rain scatter blue light, giving HD 189,733b its jewel-like appearance. It's a cruel irony, a world of breathtaking beauty, hiding an atmosphere more violent than anything in our solar system. Yet for all its fury, this glass-raining monster offers scientists a gift. By studying its extreme weather, we're learning how atmospheres behave under conditions we could never replicate on Earth. It's a laboratory for the physics of chaos, a place where the universe reminds us, even the most serene-looking corners of space can harbor storms beyond imagination. The moon might seem like a cold, distant stranger, but it's actually Earth's long-lost sibling. A piece of our own planet torn away in a cataclysm so violent it reshaped both worlds forever. This is the giant impact hypothesis, and it's not just a wild guess, it's the most compelling explanation for why the moon and Earth share such uncanny similarities. Picture the early solar system 4.5 billion years ago when Earth was still a molten newborn. A Mars-sized protoplanet named Theia, after the mythical Greek Titan who gave birth to the moon goddess Selene, came barreling toward us at 15 miles per second. The collision wasn't a gentle nudge, it was a head-on smash so powerful, it vaporized Theia and gouged out a chunk of Earth's mantle, sending a searing plume of debris spiraling into space. For decades, this scenario was just a theory, until geochemists examined moon rocks brought back by Apollo astronauts. The oxygen isotopes in lunar samples matched Earth's almost perfectly, like two fingerprints from the same hand. If the moon had formed elsewhere, its isotopic signature would have been different, like a stranger's DNA. Instead, it's nearly identical, telling us both worlds share the same raw materials. Computer simulations show how the debris from this cosmic car crash could have coalesced into our moon within just a few hundred years. Its molten surface glowing red-hot as it cooled into the familiar gray orb we see today. But here's the twist. Theia didn't just donate material to the moon, it fundamentally altered Earth. The impact likely tilted Earth's axis, giving us our seasons, and the energy released may have liquefied the entire planet, reset its geological clock. Some scientists speculate that the collision even delivered much of Earth's water, locked in Theia's minerals. Without this apocalyptic event, our world might have been a dry, lifeless rock, its days unchanging, its tides non-existent. The moon, then, isn't just a celestial companion, it's a monument to cosmic violence, a living relic of the crash that made our world habitable. Every crater, every ripple in its dusty plains, traces back to that fateful moment when two worlds became one. So the next time you gaze up at its pale glow, remember, you're looking at a piece of home flung into the sky by the universe's most destructive embrace. Most stars burn hot enough to vaporize steel, but the universe has a strange exception: objects so cool, you could theoretically touch them without being incinerated. Meet Y-class brown dwarfs, the cosmic oddballs that blur the line between stars and planets. These failed stars lack the mass to ignite full nuclear fusion in their cores, leaving them to smolder at temperatures as low as 80 degrees Fahrenheit, cooler than a summer day on Earth. Imagine a celestial body the size of Jupiter, drifting through space, radiating barely more heat than a cup of coffee. That's the reality of the chilliest brown dwarfs we've discovered, like WISE J0855, which hovers at a frosty -54 degrees Fahrenheit, colder than Antarctica. How can something star-like be so cold? Brown dwarfs form like stars, collapsing from gas clouds, but they're too small to sustain the hydrogen fusion that powers main sequence stars like our Sun. Instead, they glow faintly with residual heat from their formation and occasional deuterium fusion, a weak stellar ember that flickers out over billions of years. Over time, they cool into planet-like objects, their atmospheres swirling with clouds of molten iron and sand, their dim light barely visible even to infrared telescopes. The search for habitable worlds around these lukewarm giants is rewriting the rules of astrobiology. While brown dwarfs don't emit much visible light, they do radiate infrared warmth, creating a narrow, Goldilocks zone where liquid water could exist, just not in the way we expected. Planets orbiting them would need to huddle incredibly close, often nearer than Mercury is to the Sun. basking in the dwarf's dull glow. Tidal forces would likely lock these planets with one face perpetually turned toward their dim host, creating a world of eternal twilight on the border between scorching day and frozen night. Yet the possibilities are tantalizing. Some models suggest such planets could maintain thick atmospheres trapping heat, with climates resembling a steamy global jungle rather than the frozen waste lakes we initially imagined. Others speculate about exotic life forms evolving to harvest infrared energy, their biochemistries adapted to a sunless sky. Brown dwarfs challenge our definitions. Are they failed stars or overgrown planets? Could their faint warmth cradle life in ways we've yet to imagine? The cosmos doesn't care about labels. It serves up wonders that defy our neat categories, reminding us that even the coldest corners of space might hide the strangest sparks of possibility. Carl Sagan wasn't just being poetic when he said we're made of star stuff. He was stating a scientific fact written in the very atoms of our bodies. Every element heavier than hydrogen and helium, from the calcium in your bones to the iron in your blood, was forged in the nuclear furnaces of dying stars and scattered across the cosmos in violent supernova explosions. That oxygen you're breathing right now, it was once the breath of a star millions of times larger than our sun. The gold in your jewelry, the remnants of colliding neutron stars ejected in a glittering spray that eventually found its way into Earth's crust and eventually your ring finger. Let's break down the cosmic recipe that built you. In the early universe, only the lightest elements existed: hydrogen, helium, and trace amounts of lithium. It took the extreme pressures and temperatures inside stars to cook up anything heavier. Over millions of years, stars like our Sun fuse hydrogen into helium, but it's the massive ones, those at least 8 times heavier, that become the universe's true alchemists. In their final moments, these giants burn through elements like carbon and oxygen, layering their cores like an onion until they reach iron. That's when the party ends. Iron fusion doesn't release energy, it consumes it, starving the star of its vital support. The core collapses in less than a second, triggering a supernova explosion so powerful it outshines entire galaxies. In that apocalyptic blast, something miraculous happens. The energy is so intense it forces atomic nuclei together, creating elements heavier than iron, copper, zinc, even uranium. The shockwave hurls these newly minted elements into space at nearly 1/10 the speed of light, where they mix with interstellar gas and dust. Billions of years later, that enriched material collapses into new stars, planets, and eventually life. When Earth formed 4.5 billion years ago, it scooped up this stardust, weaving it into mountains, oceans, and much later, you. Here's the mind-blowing part: your body is recycling atoms that have existed since the dawn of the universe. The carbon in your cells might have once been part of a dinosaur, an ancient fern, or a distant galaxy. The nitrogen in your DNA could have floated in the atmosphere of a planet orbiting a long-dead star. Even the hydrogen atoms in your water molecules are primordial, the only survivors from the Big Bang itself, unchanged for 13.8 billion years. This isn't just a cool fact, it's a radical perspective shift. The same forces that sculpt galaxies and ignite supernova also assembled the building blocks of your fingernails, your heartbeat, your thoughts. When you look up at the night sky, you're not just an observer, you're the universe looking back at itself, a conscious collection of atoms that once danced in the hearts of stars. As Sagan put it, the cosmos is within us, and that connection isn't metaphorical, it's elemental, literally. So there you have it, 30 cosmic truths so bizarre, they make our everyday reality feel like a dull sideshow. From diamond planets to singing black holes, invisible dark matter to moons made of Earth itself, the universe has proven itself stranger than anything we could dream up. And yet, here's the humbling twist: everything we've uncovered is just a fraction of what's out there. The Milky Way alone holds billions of stars, each with its own secrets, and beyond that. 2 trillion galaxies, each a sprawling island of mysteries waiting to be unraveled. Think about it, every atom in your body was forged in the heart of a dying star, and the very laws of physics that govern your existence also sculpt galaxies. You are, in the most literal sense, the universe observing itself, a fleeting spark of consciousness in an epic 13.8 billion year story. That might sound overwhelming, but it's also oddly comforting. No matter how small we seem in the grand scheme, we're woven into the cosmos in ways we're only beginning to understand. The best part, this isn't the end. Every discovery peels back another layer, revealing new questions, new wonders. Maybe one day we'll crack dark matter's code, or find life on an exoplanet, or even uncover evidence of parallel universes. Until then, keep looking up, stay curious, because the universe isn't just out there, it's in you, around you, and everywhere in between. Now, over to you. Which of these truths rocked your world the most? Was it the black hole's eerie hum, the moon's slow escape, or the fact that 95% of the universe is missing? Drop your pick in the comments, and who knows, maybe your answer will inspire our next cosmic deep dive. The universe is full of surprises, and the next big revelation could be just a question away.